Good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Walter Chapman. He is currently the William Akers Professor of Chemical and Biomolecular Engineering, the Director of the Energy and Environmental Systems Institute, and Associate Dean for Energy Research at Rice University. Among his several contributions, Professor Chapman is famous for the development of an equation of state for associating fluids called SEFT. Together, his three main papers about equation of state for modeling associating fluids have more than 5,000 citations. Chapman's research group uses tools such as molecular simulation, computer visualization, statistical mechanics, and nuclear magnetic resonance to discover how material properties and structure depend on molecular forces, focusing on polymer solution and plants, associating fluids, confined fluids, natural gas hydrates, and alpha phosphoteins. Nowadays, Professor Chapman has more than 360 publications with more than 5,000 citations. So once again, thank you so much, Professor Chapman, for being here. You can feel free to start the presentation.
Great. Thank you so much for giving me the opportunity to talk today. Let me find, let's see if I can find the pointer. Oops, here we go. Okay, so what I'd like to talk about today is something I've been playing with, actually thinking about for a while, but really did over the pandemic. So my interest is in understanding, I guess, the behavior of fluids and deviation from ideality. But what I found was that there's something that was missing in thermodynamics, and it's actually kind of fun. So this is rather than talking about equations of state in detail or talk about density functional theory in detail, I'll talk about just how we went through and analyzed this system. Is kind of a fun thing. So I'll talk about Flory-Huggins Revisited, and you'll see why. And I'll deal with solution non-idealities of polar, polarizable, and associating molecules from solvents to polymers. So I want to start off by just making sure we're all up to speed on perturbation theory. And so in a perturbation theory, what we do is we define a reference fluid for which we know the properties, and then a perturbation, which is the difference between the reference fluid and the fluid of interest. And we calculate that by considering, for example, the potential of interaction between molecules. So this phi jk is the potential of interaction between a pair of molecules J and K. So they have different components. It's given by a reference potential plus a perturbation contribution. Now, I've shown here kind of the famous Weeks-Chandler-Anderson split, where the reference fluid is shown with this repulsive interaction, and the perturbation is given by the attractions. And so this in this equation, the alpha parameter, if it's 0, we have a reference fluid. If we have 1, it's the full potential. And so we can perform a perturbation expansion for, say, the Helmholtz free energy, and say the Helmholtz free energy is the free energy of a reference fluid plus, say, the first order correction plus second order correction, and so forth. In the first order correction here, you've probably seen this, and many of you, we write down just an integral of the perturbation part of the potential times the reference fluid distribution function. And the reference fluid distribution function I've shown down here is the really is just the density distribution of molecules. So it's the density of molecules, a function at a distance r away from a particle that's at the origin, and it's divided by the bulk density. So this sort of perturbation expansion is just what van der Waals did in his famous equation of state, describing the pressure of a fluid is given by the pressure of a repulsive fluid plus the difference in pressure due to the attractions between molecules. I want to point out, and I'm introducing this just to make sure we're all on the same page, but the free energy then is explicit in number of molecules, volume, and temperature, or you might think of in terms of density and temperature. And if we need to solve for the volume at a specific pressure, this is generally an iterative solution. And this comes into play when we define excess properties, for example, in thermodynamics, because we need to know the chemical potential of the fluid, of a component in a mixture at a certain pressure, and the chemical potential as a pure fluid at the same pressure. And that's why I want to introduce this. Now, we take advantage of these perturbation theories. As I showed, that was just one. It was called the high temperature expansion. But there are various perturbation theories that allow us to write down the equations of state of fluids. And for example, here's the polar PC-SAFT model. We start with a reference fluid. So reference fluid is maybe hard spheres in this case. We could also use Lennard-Jones spheres. We've also used Soave-Redlich-Kwong spheres. You can essentially use as you wish. You can then, using Wertheim's theory for associating fluids, as I extended it in my thesis work in proposing the SAFT model, you can describe the change in free energy due to chain formation and the change in free energy due to association. Gross and Sadowski developed a segment-segment dispersive free energy contribution based on molecular simulation results for square wall chains. And then more recently, Prasanna Jog and I developed a dipolar chain theory, which allows you to deal with multiple dipolar moments along the chain-like molecules. Now, I'm introducing this because this is the type of model that we might need in various engineering applications. And so I'm not going to get into detail of any of these models, but I just wanted to introduce this because when we're dealing with, in the downstream, thermodynamic modeling, we need to understand the effect of association, molecular size, shape, maybe polar interactions, as we're describing, say, separations, the phase splitting and resulting deposition, which can cause problems in reactors or heat exchangers or flow lines. And we're interested in phase behavior because that allows us to create, say, self-assembled materials. So we need to understand phase behavior over a wide range of temperature and pressure, and as well as interfacial properties and self-assembly. But this is kind of the challenge that chemical engineers have to deal with, particularly in the downstream where you are in the chemicals area. You may be dealing with molecules that have polar interactions like ketones, ethers, esters, and others. You may be dealing with hydrogen bonding molecules that not only have multipolar interactions, but also have hydrogen bonding interactions like water alcohols. You may be dealing with molecules with large size asymmetry like polymers, asphaltenes, brine chemistry, and so forth. In many cases, particularly in the chemical side of the industry, we're using activity coefficient models. And the activity coefficient models, rather than, say, Peng-Robinson or Soave-Redlich-Kwong equation of state, because you're dealing with molecules that have multipolar interactions or association interactions or large size asymmetry. And so you avoid some of these cubic equations of state. Instead, you use activity coefficient models, but the activity coefficient models like NRTL, Uniquac, which say the most commonly applied in industry, although they're now applicable or do a better job when we're dealing with polar interactions, they don't necessarily separate the polar interactions from the dispersive interactions of the molecules. And more recently, people have found that they don't, because they don't deal well with hydrogen bonding fluids, groups are taking the hydrogen bonding term from SAFT and trying to marry it into an activity coefficient model. And the approximations that are being made are questionable at best. And we want to be able to model these sorts of systems, we really need to break out the dispersive from the polar interactions and hydrogen bonding interactions, because they have different dependencies on temperature, and they have different compositional dependencies as well. So if we're dealing with acetone interacting with normal pentane, it's not only the van der Waals interaction between acetone and pentane, but the fact that acetone can interact with other acetone molecules through this dipole moment on the carbonyl oxygen. But if acetone interacts with chloroform, we of course know there's a strong cross association, because the hydrogen in chloroform is partially positively charged, the oxygen in acetone is partially negatively charged. And in industry, there's a motivation for these new activity coefficient approaches. As I said, they've taken the SAFT association term and added it to NRTL or Uniquac, for example. But then there's a question of consistency between activity and fugacity coefficient models. And what we'd really like to do is have not only consistency between the models, but we'd actually like to use the same parameters when switching between the models. We want to be able to handle polar interactions, hydrogen bonding, also induced dipoles, and polymers in the same with the same models, both in terms of fugacity coefficient and activity coefficient. And we want to have physical parameters, so we can calculate these parameters from molecular interactions. And so this is kind of the wish list, right? And we want to have models that are verified versus molecular simulation, where the lattice-based models, NRTL or Uniquac, it's, say, we can compare with lattice-based simulations, I suppose, but we'd like to really compare with continuous space simulations. And so it seemed to me that the answer is, rather than trying to add the SAFT association term to an activity coefficient model, why don't we have activity coefficient models that incorporate these molecular theories that have been validated versus molecular simulation? So that's what I would really like to do. Now, as I said, people have started to do this sort of thing, but they've taken a rather traditional approach, decades old, last century, in fact, last millennium type of approach. And that is that they write that the excess Gibbs energy is the excess Helmholtz free energy plus pressure times the excess volume. And this is just thermodynamics. We're all comfortable with this. And then what they do is they say, well, pressure times excess volume term we know is going to be small. Why don't we assume it's equal to 0? And then we'll write that the excess Gibbs energy is the same as the excess Helmholtz free energy. And that's all fine. And that should be a reasonable approximation. But then it is tempting to write that the excess chemical potential is equal to the pressure, the partial of the excess Gibbs energy with respect to mole number at fixed temperature, pressure, and mole number, holding all other mole numbers constant. Of course, this is perfectly fine. But then it's written this way, that the partial of the Helmholtz free, excess Helmholtz free energy with respect to mole number at fixed temperature, pressure, and mole numbers. But that's not correct, because then if you took that derivative, you'd end up with the partial of the Helmholtz free energy with respect to mole number at fixed temperature, volume, and mole number, all other mole numbers held constant, which is the excess chemical potential. And you end up with an extra term, minus pressure times partial molar excess volume. And I can't trace back. I know this was done in the 1990s by a famous thermodynamicist, but I think it's been done for a long time. And this equation is incorrect. The chemical potential is not equal to the chemical potential minus pressure times the partial molar excess volume. And so I went out and wanted to do this correctly, and I'm embarrassed to say it took me a long time, but I'll show you a very simple way of looking at this. And you actually end up with some rather interesting results. So, as I said, this is not true, right? So let's start very simply. The fugacity is given by the mole fraction times fugacity coefficient times the pressure. We know this is exact. We can also write, or more commonly for in the downstream, the fugacity is given as the mole fraction times the activity coefficient times the fugacity coefficient of the pure component at some pure component pressure, typically the vapor pressure, but it could be any pressure, and then a Poynting correction, which corrects for the fact that this fugacity coefficient of the pure component at a pure component pressure is the fugacity at this pure component pressure, but we need the fugacity at the mixture pressure, so apply the Poynting correction, right? Now we can write that the log of the fugacity coefficient is given by the residual chemical potential of the mixture, and this is residual. I need to be careful. It's residual to an ideal gas at the same temperature and molar volume as the real fluid. So it's an ideal gas evaluated at the same temperature and molar volume as the real mixture. And then there's a minus log Z to give us the log of the fugacity coefficient. So we can write that down, and we have this exact expression. So the log of the activity coefficient is given by this relation. Now again, one of the difficulties that I've always had to calculate the excess chemical potential or the activity coefficient is I was thinking I needed to have the chemical potential of the component I in the mixture and chemical potential component I in the pure fluid at the same pressure. And to do that, I would need to iteratively solve for the density that gave me the same pressure. But really just thermodynamics tells us that we can write this down, and even though, say, the chemical potential of component I in the pure component is not at the same pressure as the mixture, I have a Poynting correction. So I can correct the chemical potential to be at the same pressure as the mixture. Now it's common to say that the molar volume of the pure component is relatively independent of pressure. So this is molar volume of the pure component in the liquid phase. We say it's relatively independent of pressure, and so we can perform this integral and give this result. And of course, this is true as long as we're far enough away from any critical point, so that we can assume the molar volume of the liquid is independent of pressure. And the pressure range needs to be small as well, so that we can take this molar volume out as a constant. And so this is an approximate expression. But what's interesting is, given the molar volume of the mixture, or an estimate of the molar volume of the mixture, and the molar volume of the pure component, this expression allows us to very quickly calculate, even from an equation of state, the activity coefficient. And so we call this SAFT AC, for SAFT activity coefficients. Now what's interesting is SAFT AC now includes, and I'll point out, I need to know the molar volume of the mixture, molar volume of the pure component. I can approximate them as I want. And I need to, but this is very fast. I just simply put in the mole fractions, the molar volume of the mixture, the temperature, and this is a direct calculation of the chemical potential, direct calculation of the chemical potential of the mixture, same thing for the pure components. So this is it turns out it's a fast way of calculating activity coefficients. And SAFT AC includes explicitly hydrogen bonding, includes polar interactions, can include induction, which are all missing from NRTL and UNIQUAC. Not only that, using an equation of state in this way allows me also to very quickly calculate the compressibility or isothermal compressibility of the system. And so I imagined that we could have smart simulators, because for now, we input an activity coefficient model. The simulation does the thermodynamics based on an activity coefficient model, even in processes where the fluid is highly compressible, and so the activity coefficient model doesn't apply. But we could, based on this sort of approach, we could lead to smart simulators, which can switch from an activity coefficient approach to a fugacity coefficient approach when the system is compressible. And so, and if we use this, our activity coefficient model would be the same model as the fugacity coefficient model when we want to switch for the process simulator. So it seemed to me that this would be an advance in doing smart simulations rather than what we're doing now. And so the model is given in this industrial and engineering chemistry research paper. But we can take this a little farther, and it becomes really interesting. This is the pressure of the mixture and the pressure of the pure component. We could write this as the pressure of the mixture is given by the pressure of an ideal gas plus the residual contributions, or the contributions due to the interactions between molecules. And if we do that, so we start with the same expression, I could write that pressure is given by RT plus the RT over V, the ideal gas contribution, plus the residual contribution. And if we write that, we end up with this interesting expression. You'll recognize this very first term. This is a Flory-Huggins type combinatorial term, but it's a thermodynamic term. In other words, Flory and Huggins, although they derived their term using a lattice theory, it's actually an ideal gas contribution. It's a result of thermodynamics. I don't think anybody's been aware of this. If you go back to Hildebrand, and I think more recently Richard Elliott, I know, has shown that you can get this Flory-Huggins type term out of the van der Waals equation of state, for example. But as it turns out, of course you can, because it's just a thermodynamic, it's an ideal gas contribution. It's present just from thermodynamics. I call it a Flory-Huggins type term because it's not exactly, Flory and Huggins used segment fractions, not volume fractions, because they derive this based on a lattice. And I'll talk about that soon. But notice this does not require us to assume that the excess volume is equal to 0. The only assumption is that the molar volume of the pure component is independent of pressure. And then we obtain this result. I find it rather fascinating because this is not what I'm taught in thermodynamics courses. Now, we can go back to an equation of state now, polar PC Saft. And I want to do this because I want to start evaluating the terms in this model. Notice in the polar PC Saft model, we have the free energy is given by the free energy of the reference fluid plus the chain term, dispersion term, association term, and polar term. And the approximation that we've ended up with is that this is a linear combination of different terms. So what we can do is we can write down that the activity coefficient is given by a linear combination of terms. Ideal gas, which is the Flory-Huggins term, or Flory-Huggins combinatorial term, a hard sphere term, chain term, dispersion term, association term, and dipolar contribution. Now, what's interesting is the pressure is also a sum of terms. So I'll have a hard sphere contribution to pressure, a chain contribution, dispersion, and so forth. So we can consider now each of these individual contributions. For example, here's the hard sphere term. Hard sphere term is given by the chemical potential of hard sphere in the mixture. I've simplified this because the pressure of the pure component combined with the chemical potential of the pure component gives us the Helmholtz free energy of the pure component. And here's the hard sphere pressure for the mixture. Now, let's only consider this mixture. And essentially, this gives us the Saft AC contribution to the activity coefficient. But we could choose how we choose the molar volume of the pure component and the molar volume of the mixture to maybe simplify these equations. And so that's what I'd like to do. So here's the general form for the log of the activity coefficient due to the hard sphere contribution. And again, if you go back to Hildebrand and others in history have tried to look at what is the correction to the Flory-Huggins term due to hard sphere repulsion or other contributions, but we can write them down directly now. And this actually is a fairly simple derivation. I know it's an ugly term, but as I said, maybe we can choose the molar volume of the mixture and the molar volume of the pure component to simplify the equations in some way. So let's just imagine hard sphere mixture. And if I wanted to simplify the hard sphere mixture, what I would imagine is all the hard spheres are the same size. That would be the simplest, right? This is general for different size hard spheres, but let's just say all the hard spheres are the same size. And if they are all the same size, then let's say some of them are red and some of them are blue, so it is a mixture. I want to know the log of the activity coefficient for the red spheres. But if they are all the same size, then it turns out they form an ideal solution. I'm not talking about the association term, the polar term, all the other terms. Let's only focus on hard spheres. Hard spheres of the same size form an ideal solution. And so if all the diameters are the same, log of the activity coefficient is equal to 0. The activity coefficient for the hard sphere fluid is equal to 1. And in such a mixture, the pure component and the mixed system have exactly the same packing fraction. To be at the same pressure, they must be at exactly the same packing fraction. So let's imagine that we're going to evaluate the chemical potential of the pure component and the mixture for equal size spheres at the same packing fraction. So we can then look at the chain correction to the Flory-Huggins term. The chain correction involves a distribution function for the hard sphere fluid. Here's a derivative of that distribution function with respect to density of component I, another derivative, another contribution. G hard sphere of I, or for component I rather, is the reference fluid radial distribution function. Here for hard spheres, it's evaluated at a certain distance, which is the bond length. And again, this is the above is general. This is the for the activity coefficient for SAFT AC, which will give us activity coefficients consistent with the polar PC SAFT equation of state. But now I want to simplify this. So again, let's imagine that we have equal diameter hard spheres, and we're going to evaluate the properties of the mixture at the same packing fraction as the properties of the pure fluid. Now, if all the hard spheres have the same size, then GII hard sphere is the same as GJJ hard sphere. And if they're at the same packing fraction, then G of R in the mixture will be the same as G of R for the pure component. And so if we do that, we actually find that log of the activity coefficient for the hard chain contribution, for the chain connectivity contribution, in this special case is equal to 0. And so this gives us what we call SAFT-SAC, SAFT simplified segment-based activity coefficients, all right? So this simplifies for equal diameter spheres and for fixed segment density to that the log of the activity coefficient, we still have the Flory-Huggins term, but now we have a dispersion term, an association term, and the dipolar contribution. Now, notice that the Flory-Huggins term, instead of volume fraction, I now have it in terms of segment fractions. M is the chain length of the molecules, and so this is the segment fractions. This is the true Flory-Huggins term, where segment fractions and not volume fractions must be used to cancel the SAFT, hard sphere, and chain terms. So again, Flory-Huggins doesn't require us to assume no change in volume and mixing, but it does require us to assume that the molar volume of the pure component is relatively independent of pressure. And now we have exactly the Flory-Huggins contribution. Now, using perturbation theory, in fact, that first order perturbation theory that I showed you, we can derive a term, a dispersion term that's similar to the Scatcherd and Hildebrand regular solutions theory. As long as the segments are all the same diameter and we're at fixed segment density. Again, without assuming no change in volume and mixing. So I would say that it's fortuitous that Flory and Huggins derived their approach on a lattice, which is at fixed segment density, or fixed segment density, fixed segment fractions. But we find the approach applies to mixing at fixed pressure with excess volume equal to 0, not equal to 0. In fact, I would claim that the reason that Flory-Huggins theory is actually useful is because of this fortuitous, and I don't think Flory or Huggins or Hildebrand or anybody has ever been aware of this, that the theory is actually valid for mixing at fixed pressure, or mixing. It's valid for mixing at fixed pressure, because fortuitously the contributions cancel in this limit. In fact, this resolves a paradox from this paper in 1994 that Sanat Kumar wanted to show polymer scientists. He told me, Sanat told me one time that polymer scientists believe that there is no change in volume on mixing because Flory told them that that was true. And so you cannot tell a polymer scientist that there could be ever change in volume on mixing. And he wanted to show that actually changes in volume on mixing were important to include in your free energy. And so what he did was he performed molecular simulations of a mixture of a Lennard-Jones chain and another Lennard-Jones chain. They're identical chain lengths. And he performed the simulations for mixing at fixed density and for mixing at fixed pressure, at constant pressure. And he found the paradox that Flory-Huggins theory works at fixed pressure, but it does not work at constant volume, in this case, or no change in volume on mixing. And he found that to be rather surprising, and I don't think anyone has resolved this paradox, but in fact, this does. That Flory-Huggins theory fortuitously actually works even when you have change in volume on mixing. In fact, based on this derivation, it does assume that the segment densities are all the same, and we must use segment fractions and not volume fractions in the combinatorial term and in the other terms as well. So we can take this further. What about the Saft association term? Well, the Saft association term, it turns out, if we assume all the segment diameters are the same, and we perform mixing, or we evaluate the mixture and the pure component at the same segment density or packing fraction, then we end up with a very simplified form for the activity coefficient due to association. But note that the segment fraction here is used and not a volume fraction. Now, others have derived a similar but different equation, but it's been through this cancellation of errors where they've gone through and assumed no change in volume on mixing, and that ends up causing you to, well, some thermodynamically inconsistent equations. I'll just simply say their assumptions are not clear, and it can lead to potential errors. What's interesting is the equation they end up with, because of these cancellation of errors, is essentially the same. But I must point out, this must be a segment fraction rather than a volume fraction. Of course, in many cases, you might be able to use a volume fraction as a good approximation to the segment fractions. Now, I won't bore you with equations. We can do this for the PC-Saft dispersion term. We can do this for dipolar chain theory. And we can do this for what are called phantom dipoles, which is due to Ben Marshall. And I'll show you some results. Now, what's interesting is I said that the regular solution theory works out well. You can get regular solution theory from the Gross and Sadowski dispersion term, but you have to assume that the chain lengths of the two molecules are the same. And I think you'll find, if you develop the perturbation theory, that it would be to be most accurate, you would have to assume that for the regular solution theory to be accurate, the segment, the chain lengths of the molecules would have to be the same. But of course, you can approximate that the chain lengths are different. But PC-Saft includes the chain length contribution in their essentially in their pair correlation functions. And so, but you can derive that. So I'll show some results. So Saft AC reproduces the activity coefficients of SAFT, of polar PC SAFT equation of state, as long as pressure is low. And pressure needs to be low so that we can use this Poynting correction type term. I was always told that activity coefficient models should not be used above maybe 10 or 20 atmospheres because they fail, but no one's ever told me why, but now we can see why that actually occurs. So SAFT AC, because it includes the association and the polar terms, can match infinite dilution activity coefficient and produce accurate vapor-liquid equilibrium. We showed two examples here for ethanol hexane, where Uniquac, NRTL will do the same, gives you false liquid-liquid phase splitting because they cannot match the infinite dilution activity coefficients and match the rest of the phase behavior. It's important to be able to match the activity coefficients as you approach infinite dilution, because that's where most of the trays in your distillation column are going to be. And so you need to be able to describe the phase behavior, say, under those conditions. Here for this is a diketone in cyclohexane. SAFT does a nice job of describing this, or polar SAFT does a nice job of describing the phase behavior. Here, Uniquac fit, or in fact, Unifac, fit to the infinite dilution, well, is not able to describe this. I guess it's actually not fit, but it's not able to describe this because we have multiple functional groups. Unifac is really developed for systems with single functional groups. And so it starts to fail. But the what's nice is that with polar PC SAFT, we can deal with multiple polar groups or multiple associating groups. Seems to me to be a much better activity coefficient model. We can compare here SAFT SAC versus SAFT AC. And SAFT AC produces nearly identical results to polar PC SAFT. As expected, when the pressure goes above 10 to 20 bar, both of these models deviate from polar PC SAFT. It's hard to see, truthfully, but maybe in this curve you can see best. This is ethanol with normal heptane. The dashed is the SAFT AC, or polar PC SAFT equation of state activity coefficients. The solid line is what you get from SAFT SAC. And so the phase behavior is well reproduced by both approaches. Similarly here for butanol with normal heptane, you can see deviations over here between the SAFT AC versus the SAFT SAC model, right? Now what's interesting is, since now we can determine the idle gas or the Flory-Huggins combinatorial contribution, hard chain contribution, dispersion, association, dipolar contributions, we can break these out and we can look at what the log of the activity coefficient looks like in terms of these various contributions. And here for ethanol and here for heptane, we can see that the dipolar, dispersion, hard chain, idle gas contributions kind of cancel each other out. And you can't see, but the dashed curve is the total contribution. It's the dark thick line is the association contribution. So for this alcohol-alkane system, the activity coefficient seems to be dominated by the association contribution. Now, what's interesting is we can look at infinite dilution activity coefficients and with this model as well, and describe how those behave and how those can actually be independent of the solvent in some cases, and which agrees with experiment. What's interesting here is I look at the case of phantom dipoles, and this is based on work by Ben Marshall. He uses dipolar chain theory by Jogue and Chapman, but what he then does is he recognizes that if you have something like a butadiene with acetonitrile, the butadiene has this double bond, and if you mix a butadiene with an alkane, it behaves like an alkane, right? And so you can have nearly ideal solution behavior. But the butadiene interacts with the dipole of the acetonitrile through that double bond. So the pi electrons in the double bond can be polarized by the electric field generated by the acetonitrile. And that polarization can induce a multipole, right, on the, and it's here modeled as a dipole, and Ben calls it a phantom dipole. So it's a dipole that can interact between the butadiene and the acetonitrile. So they actually attract each other more than you would expect. It's phantom because butadiene with an alkane doesn't include a dipolar interaction. But in the presence of these polar molecules, the double bond can be polarized, or a triple bond can be polarized. And so what Ben Marshall has found is that you include a single parameter to describe this polarization. I think it's 0.6 or so for a double bond and maybe 1.5 for a triple bond. And for any triple bond, any double bond, even in a benzene, and you include these, and you can produce phase behavior that looks something like this, using the Joe-Chapman dipole chain theory. And so it's, as Ben said, it's almost for free. And of course, this is not something that you would see in an NRTL or a Uniquac or anything like this. This is actually predictive type of phase behavior. So I want to conclude, and so what we've done is provided a simple derivation and extension of Flory-Huggins theory. I actually now respect Flory-Huggins theory a lot more. I feel like I understand where it comes from. We explain why the theory is accurate when there is a change in volume unmixing, which I think is important. And again, Flory and Huggins, I don't know that they were ever aware that what they had derived was useful, not because of this fortuitous, say, cancellation or this fortuitous result. We showed corrections to Flory-Huggins theory for associating molecules, dipolar interactions, even induced dipole interactions, as well as the dispersion term. The model provides consistency between the activity coefficient model and the full equation of state. The model includes physical molecular parameters. The model has been validated versus molecular simulation results, so we're confident over the range in which it will work. And this is really just the start of linking workflows. I see from activity coefficient models to fugacity coefficient models to molecular simulation, as well as to inhomogeneous systems. And so we're looking at extensions of this. In fact, I think that these ideas are in some way the reason that in dissipative particle dynamics that people do calculations at fixed density or fixed segment density, essentially fixed packing fraction. And they find that they get the best results if all the segments have exactly the same diameters. And self-consistent field theory, I think, is also built based on these same ideas that, as far as I know, were never known. And so I welcome questions, interactions. These are funding agencies, and really the Welch Foundation is really kind of set the foundation for me being able to think about a lot of these things. So I welcome any questions you might have, and and thank you for attending.
Thank you, Professor Chapman, for the presentation. We're now open to questions. If you want to participate, please enable your microphone or write it down at the chat and we will read it. Also, our YouTube viewers can write it down, of course, too.
João is asking. João.
Sure, Professor, go on.
Well, Walter, that's a fantastic work. Congratulations. I'm very impressed. It's great that someone, after that many years, comes up with another new approach to a model for activity coefficients. I mean, between UNIFAC and today, the only contribution that we had was basically Cosmo and nothing else. So this is really a most welcome and interesting approach that you are presenting here.
Thank you.
Now, from the conceptual point of view, I think this is great and it's very helpful. I mean, the way you come to understand and rederive the Flory-Huggins shows that. But from an engineer point of view, I can't understand what is the point of going back to a gamma-free approach when with SAFT using the 5i approach, you could describe this system. So what are we gaining from an application point of view? That's my first question, and then I will have another one.
Okay, well, thank you so much for attending. I really appreciate it. I will tell you that my co-author, Wael Fuad, I should have introduced. He's at King Fahd University. So Wael has told me that he will never do the equation of state calculations again because this is so much faster. And one of the concerns in dealing with SAFT, dealing with the full equation of state, are performing the calculations where you have to iterate to get the liquid density or the to generate at a certain pressure. So that's one of the advantages. I've talked to people in industry, and they've told me that just in terms of performing calculations, this can be can remove issues. For example, when you're doing equations of state, you guess pressure, you get a negative, or guess density, you get a negative pressure. You then have a log of negative pressure. It causes, maybe conversion issues. You don't have that in this sort of approach. People have suggested that for dynamic systems, where you're doing a process where you're doing transients in your process modeling, you don't want to go through and have to solve multiple times for roots of equations of state. This takes very, very long time. If you can simply put in values and perform the calculations, this is going to make those sorts of simulations much more affordable to do. In a reactive distillation system or reactor systems, when you're dealing with say chemical equilibrium and phase behavior at the same time, it's been suggested to me that this is going to be much faster to do. And as I said, Wael Fuad has told me that he never wants to use the equation of state again. This is just way too fast. But you're absolutely right. In terms of the thermodynamics, it would be better to use the equation of state. It's certainly just as valid, but it's the computational time that I think gets in the way.
Now, again, and you and the others will excuse me for the second question, but it's also from a very practical point of view.
Okay.
We have been using SAFT. If we are it's about the parameterization. Are the parameters transferable from SAFT equation to this approach? If we have a completely novel compound, how should we parameterize that compound? And finally, SAFT, it works when you have a Kij or some sort of interaction parameter to fit your data. Right. Where is this parameter here? How do we tune the equation to fit the data?
So the parameters are the same as the bulk SAFT equation of state. So what we find is that you might need to tweak the Kij slightly to obtain, say, good agreement over, say, a range of temperatures, a range of pressures. But the equation of state parameters are the same as the bulk SAFT equation of state parameters. Kij, which is correction for the dispersion term, comes in as the same. The issues that you have in dealing with cross association, where you may need to estimate the cross association energy and the bond volume for cross association, you still have the same issues there. Things are a little better maybe for the for dipolar molecules. Although the SAFT-SAC, which again is a very much simplified model, but I wanted to develop something that was was even simpler, right? SAFT AC is going to give you very similar results to the bulk equation of state. But SAFT SAC, we've assumed all the segment diameters are the same, but of course we don't want to give up the different segment diameters when we fit properties of the pure fluids. And so what we've done is essentially come up with a way that we're evaluating the packing fraction is the same, but the segment diameters are not necessarily the same, and so we can get a good approximate results. But with SAFT SAC in comparison with SAFT AC, but or the full equation state, the results do not seem to be all that sensitive to this assumption that all the segment diameters are the same. We still use different segment diameters. We still use the same equation state parameters. But again, the SAFT AC, which is, we're not assuming anything about segment diameters. That's always available, and it's a fast way of performing the calculations. And I'll say is, again, the other thing I think that's very useful is the idea that the process simulator can now be smart and tell us when the fluid is so compressible, we need to switch to the equation of state.
Well, it didn't answer one of my questions, that is about the parameterization of novel compounds. Do we still have to resort to the SAFT equation if we want to parameterize a new compound? Or is there a new way to parameterize a compound for this new approach?
We have not developed a new way of doing it. I would still use the conventional method of hopefully having vapor pressures and liquid densities or this sort of data that we can correlate the parameters. It may be possible to do some other things, and so we're looking into some of these possibilities. I tell you that with some trepidation, I give you this SAFT SAC equation, because if an engineer just gets that equation, they can choose lots of parameters and fit lots of data, but those parameters might not, if you then put them in polar PC SAFT, you might not get the right vapor pressures and liquid densities. And so the model might be too flexible now with if you take SAFT SAC as a completely separate model. So I think it's best to use the model in coordination with the full equation of state.
Okay, thank you. It's fantastic work. It's really.
Thank you. Thank you so much, and great talking to you.
Speechless. Thanks a lot.
Okay. Other questions?
So anyone wants to ask another question?
I have a silly one. My question Coutinho asked already, so I switch for electrostatic interactions. Are you include this in your model in near future?
For electrolytes?
Yes.
Yeah, that's the. I've been thinking about that. That's the next thing to do. We've looked at this. Yeah, we're starting to look at that. But we're not there yet. But that is the goal. When I was a younger professor, I'm still young. When I was a younger professor, we write this what's called a career proposal, or basically, and so what will I do in my career? And I've done everything except I also said we're going to do polymers in solution with electrolytes and inhomogeneous systems. So we can do everything so far, except I need to be able to do electrolytes and maybe polyelectrolytes. So that's still working on it. But yes, that is direction I'd like to go.
Thank you. Very nice work.
Thank you. Yeah, I'm hoping it changes the way we maybe even teach thermodynamics to some extent. I was never going to give the 3 pages of derivation to get the Flory-Huggins combinatorial term, but this is just a few lines. So yeah, but I'm also interested to find out, has no one else done this? It's not hard.
The derivation is not wrong when you think about Let's model. Mm-hmm. The derivation is not wrong.
Yeah. Yeah, I'd like to hear if people have. I know Richard Elliott, for example, has done work showing that the Flory-Huggins combinatorial term comes out of the van der Waals equation of state, but I had not seen anything. I had not seen anything like this, and so I think putting this all together is. We'll have to see if it catches on with engineers, right?
For sure. Well, does anyone still have another question?
No, just a comment. In Brown's book, they show how to derive activity coefficient model from equation of state. But there is completely different because they made approximation already at the beginning. So it's not the same approach.
Right.
But,
yeah, actually, yeah, send me that reference. I'd like to take a look just to see. I can't say that I've looked extensively. I haven't really paid a lot of attention to activity coefficient models in the past, just to teach them. And so, yeah, but as I have gone back and looked at some things, I haven't seen anything similar. I'm interested to look back and see what people have done when they've done like Haran-Vidal or Wong-Sandler mixing rules and how that is justified, because anyway, it would just be interesting to see. So.
Okay. So I think our time is almost over, and I want to thank you everyone for the discussion. And once again, thank you, Professor Walter Chapman, for the presentation.
Oh, you're certainly welcome. And again, thank you so much for the opportunity to share.
It's a pleasure. So our seminars are being recorded and posted on YouTube, of course, after the invited lecturers agreements. Please check them out on our YouTube channel. And this is our organization committee. We are responsible for inviting and communicating with the lecturers. We also handle social media, video editing, certificate writings, and hosting. Thank you all for being here today, and we will meet again next Thursday at the seminar that will be given by Professor Georgios Kontogeorgis, entitled Recent Developments in Thermodynamics of Water and Electrolytes. See you there.